Okay, so now we want to discuss this more general case, which is if you have several outer balance masses act independent transverse planes, uh, and which are displaced along the length of the shaft. So as you can see, you have these three masses: M1 with angle theta 1, M2 with angle theta 2, and M3 with angle theta 3, all with this horizontal plane. And this is also the side view is given, M1, M2, and M3, and the angles are given. And here our objective is to find out MARA and MBRB, which can be in these two locations, so that the system is totally balanced dynamically and as well as statically. So if the system is dynamically balanced, it will be balanced statically automatically. So the thing is, the shop is also rotating at angular velocity omega. So if the system will be balanced dynamically, uh, there will be no forces here on the bearings, and which is what we want. So now this is a very important point here, that if we want that our system is dynamically balanced, so we need to satisfy any two of the following conditions. So there are three conditions given here. The first condition is summation of all the moments about AA equals 0. So this is the AA. So we will take the moments about AA, and we will make sure that these moments are equal to 0. And if we use this equation, it will provide you with the MBRB. Similarly, you can use moment about BB, which is this location here. So if you take the moments about BB, this will provide you with the value of MARA. Now you can also use this third condition here, but if you use one of the moment condition, and then you can use the forces condition. So you don't need to use both the moments condition, because normally it's straightforward to use forces rather than moments. So if you use equation 1 and equation 3, so you can get the same results, or either you can use equation 2 and equation 3. Uh, you can also use equation 1 and 2. So you can use either of equation 1 2, or 1 3, or you can use equation 2 and 3 to find out these unknown masses and their locations. Now, as you can see that, remember that if the system is dynamically balanced, there will be no out of balance reaction forces at the shaft supporting bearing. So this is our main objective here. So now we will show the process here before going to solve some actual numerical example. So this is to show you how the whole process works. So as you can see in this case, that we are just taking the same example here, and you have three masses, M1, M2, and M3. These are out of balance masses in the system here, which is displaced along the shaft. The location of these masses are given. M1 location is given as R1, R2, and R3, and their angles are also given. Okay, so now what we will do, that we will start uh, with the omega square equal to 1, because we can draw the forces here. So we know that F1 is equal to F1, we know that it is equal to M1 R1 omega square. Similarly, F2, which is the centrifugal force of mass 2, is M2 R2 omega square. And F3 is again M3 R3 omega square. So first we will start with the omega equal to 1. So this means that we will just use M1 R1, M2 R2, and M3 R3 for the forces. So the M3 is F3 is acting in this direction, and F2 is acting in this direction here. Okay, so now we first want to calculate. So the requirement here is that we want to calculate the uh, two masses and their location. So that is objective here is to calculate MARA and MBRB. So as we discussed earlier, that we can use these condition here, the summation of all the moments at BB equals 0, and we can use summation of all the moments at AA equals 0, or summation of all the forces equals 0. So in this case, for example, if we just use the maybe the first condition here, so summation of all the moments at BB equals 0. So if we use this condition here, so this means that we will be taking moments about this point here from the location B. And what we can do here is that we will take the moments of all these forces. So the moment of F1 will be equal to the force multiplied with this distance here, which is d1. Similarly, for F2, the distance is d2 from B, and similarly for F3, the distance is d3. And now what we can do here, that if we just draw the horizontal line, and here what we want to do, that we want to do the moment vector polygon for the moment about the BB. So we want to draw the moment polygon here for calculating the, if you're taking the moment from BB, so this will provide you with the MARA. Okay, so if you start, for example, from this point here, and the first vector that you can draw is the moment of this F1, and we will draw the moment in the direction of the force here. So this will be our F1 times D1. So F1 here is M1, R1, and D1, and it's very the idea here is that we are drawing these moments in the direction of the forces. If you calculate the actual direction of the moments, which you can calculate from the right hand rule, which will be at 90 degrees to this force here, but because the shop is rotating at angular velocity here, so all the forces and moments will be rotating with the shop. So this means that their absolute positions are not important, but their relative positions are important. So that's why, for convenience, we are drawing these moments in the direction of the forces. Similarly, for the M2, now what we can do, that we can write the moments in the direction of the, so this is our theta 1, and in this case we can draw the M2 R2 D2 here, and this is our theta 2, and finally we can draw the F3 here. So F3 is going to be in this direction, and this is our angle theta 3, and the magnitude of this vector is M3 R3 D3. Okay, so now now we want to make sure that the resultant moment at AA is equal to 0. So this means that that this resultant, which should be in this direction here, so that we get a 0 resultant here. So this means that this vector is required to close this polygon, and this vector here will be the closing vector. and this closing vector will be MA RA, and we know that the distance of this AA from B is D, so MA RA D. So this will make sure that the polygon is closed and we have a zero moment here, and then this will provide you uh, with the magnitude of the MARA, and then the direction of this vector can be calculated from this angle here, which you can calculate graphically. And obviously we are explaining this a graphical procedure, so you can also solve this problem analytically, which we will explain in the next lecture. So as you can see, we did everything for omega square equal to 1, and because this vector polygon rotate at omega, so the closing vector, which is this vector here, will give the required mass times radius, which is MARA in this case, and theta values, which is this theta A, and in this case it is MARA and theta A. And again, this is important point that you need to know, that for convenience, the moments vector are drawn in the direction of the force vectors, which is at 90 degrees to their actual direction. But because every vector is drawn at 90 degree to their original direction, so it doesn't matter. But it's provide you with a straightforward procedure to calculate the direction of these forces. Okay, so now we managed to calculate MARA. Now the second part that we need to calculate is MBRB. Now to calculate MBRB, we can do a similar moment polygon by taking the moments from the MAA. So you can take the moments from AA position, but that will be, as you know, that the moment polygon is a bit complicated because you need to multiply with the D. So instead of MAA, we will just use the final equation, which is summation of all the forces equal to 0. Okay, so in this case, what we will do, that here we will just use the force polygon to calculate MBRB. Now, as we also know MARA, and we need to calculate MBRB, and MARA is now known, and which is again a centrifugal force. So FCA, which is in this location here, and now we want to calculate the MBRB. So again, for this case, we will now use the force vector polygon, not the moment polygon. So now we will be just talking about the forces. So the force, again, we will be working with the omega square equal to 1. So this means that everything will be in term of MARA. So we will not be using omega square here. So again, you can start from some convenient position here. And again, this is a graphical procedure, so you will need to do everything with reference to some scales. So if you start from this point here, so the first vector that you have is M1R1, and the direction is, so you will draw this M1R1 with some suitable scale and theta 1, and now you have this vector 2, F2. So F2 is in this direction here, and this is M2R2, and this is theta 2. In the previous case, we were multiplying with the D because it was moments, but now it's force, so which is just MR. And finally, we have M3R3. So this is M3R3, and the direction is obviously from, this is our theta 3, Okay, so now we also have a force which was at this location here, at location A. So we should also add that force here. So the force was somewhere in this direction here, because you know the MARA and theta A, which you already calculated from the previous. So this is also known from the previous slide, from the moment polygon. And again, you know that this is MARA, and this angle is the theta A. So you know theta A, and you know MARA from the previous slide. So if you know this thing, and you know these four vectors now, so obviously our aim here is to make sure that there is no resultant force here. So we will draw the final vector, which will be in this direction here. So the final vector, which is in this case will be MBRB, and this MBRB should close this polygon here. So this means that the resultant is 0 here. So this will be the closing vector. So this is our closing vector here. Uh, so this is the magnitude you can calculate from this length here, and obviously this is a graphical procedure. So you will just calculate the length of this vector, and the direction will be, obviously you will be calculating using some protector here. So this is our theta b. So if you calculate MBRB and theta b, so this is what we want to calculate. So now MBRB and theta b in the reference plane B can be found from either a force polygon or a moment polygon about AA, as we discussed earlier. Similarly, the closing vector yield the required mass time radius product and the angle, so which is this MBRB and this angle theta b. And obviously the vectors in this case are drawn for omega square equal to 1.